In this series of lectures, we are going to focus in on dynamic equilibrium, but we're going to look at it in terms of chemical reactions. So we're continuing our exploration of reaction dynamics, and we're going to build on what we learned about reaction rates and rate laws and reaction mechanisms. And we've already kind of introduced dynamic equilibrium. This is hopefully not totally unfamiliar. We've been kind of sprinkling it in while we talk about other things in chemistry. Dynamic equilibrium happens for chemical reactions, but also just happens for processes. So, some of the examples we've already seen are the dynamic equilibrium for vapor pressure. This is looking at a liquid in a closed container, and the liquid will be able to evaporate a little bit. And some number of particles will have enough energy to go into the gas phase. We'll call that evaporation. And some of those gas particles, then, once they're in that gas phase, will bonk into each other or into the surface of the liquid and they'll condense. They'll go from a gas to a liquid. And so we have a rate that particles are evaporating and a rate that particles are condensing. And when those rates are equal, the total amount of gas above the surface of the liquid in the container won't change. And so when these rates of condensation and vaporization are equal, we call it dynamic equilibrium. Change is constantly happening at dynamic equilibrium, but what we see from a macroscopic perspective is that isn't changing at all. Um, and that's the key part of this, is that there's constant change, but what we observe is no change. We saw this with solvation as well. So if we take a pile of crystals like salt and we throw them in some water, at first we'll have a very high rate of dissolving. And so some of those particles will dissolve, they'll get surrounded by water molecules, and they'll go off, and it looks like the solid disappears as it dissolves in the water. Well, as those particles accumulate in the water, then some of them will be able to recrystallize onto the solid. And so we'll have a rate of dissolving where our solid becomes the aqueous phase, and a rate of recrystallization where the aqueous particles solidify onto the surface of the solid. And when those rates are equal, we'll stop seeing the solid dissolve. Like, it'll look like it's disappearing and disappearing, and then it'll stop. And the amount of solid at the bottom of my beaker will just kind of stay the same. Now there's constant change happening. Some of the particles are constantly dissolving and some of them are constantly recrystallizing, but the rates of those two processes are the same. And so we don't see a macroscopic change. And that's dynamic equilibrium. So we've been looking at this for physical processes so far. And now we're going to apply dynamic equilibrium to a chemical reaction. Um, Now, to do that, we are going to look at reactions that they have to have a forward and a reverse. They have to have like opposites, right? Opposites must be occurring. And, and we're going to first look at reversible reactions, where we have a reaction happening in a forward direction, where our reactants collide and form products, but then also the reverse, where our products collide and form reactants. We're going to see again that, and this is what we explored in the previous lectures, that the rate of the reaction is going to be dependent on concentration. And that concentration of the reactants is going to change over time, just like the concentration of products. And that's going to have an impact on the rate of the forward and the reverse reactions. And so we'll see that same concentration dependence that'll help us understand what's going on in the chemical reaction. And we'll see that dynamic equilibrium will be reached. I'm going to highlight this. My highlighter will pick up. There we go. Will be reached when the rate of that forward reaction and reverse reaction, where products become reactants, are equal. And that'll be dynamic equilibrium for a chemical reaction. So let's break this down with reversible reactions first. So I love this reaction. It's splitting water and hydrogen combustion. So think about fuel cells in cars, hydrogen fuel cells. What hydrogen fuel cells do is they take a bunch of hydrogen gas and they burn it. And burning something is just combustion, and that means you're combining it with oxygen to form water. So we're looking here at this reaction. So this process is one reaction. We can say, okay, all my hydrogen becomes water, it combines with oxygen. Now, there's another reaction. It's splitting water. And this is the reaction that plants catalyze in the process of photosynthesis. So through photosynthesis, two water molecules are split apart into hydrogen, elemental hydrogen gas, and oxygen gas. Now look at these two reactions. They're the opposite of each other. My hydrogen and oxygen combine to form water in my combustion reaction, and my water splits apart and reacts and forms hydrogen and oxygen. And so the product of one reaction is the reactants of another reaction. And these will happen separately, but they also happen at the same time. And that is what a reversible reaction is. So a reversible reaction is when we have our reactants forming products, and at the same time, those products can collide with one another and form the reactants. We have both processes happening at the exact same time in the same space. So most of our chemical reactions fall into this category. Most of them are never going to be able to completely convert reactants into products, because some amount of a reverse reaction will take place where the products collide and reform the reactants. And so because of that, we're never going to get 100% conversion. Both of these reactions are taking place at the exact same time. But the two reactions can have different rates. So the forward reaction can have a different rate than the reverse reaction. And those rates will be dependent on concentration, but the fundamental rate, even when everything's at the same concentration, can be different. And so the way we write this typically is we have our reactants and products, which now that everything's reversible, that kind of becomes arbitrary, right? But it will be we'll be able to communicate about it based on the ratio of those rates of the forward and the reverse. And we're going to use two arrows to show that something's reversible. So we've been talking about reactants going to products with one arrow. And here I'm showing two arrows, one going the forward direction, one going the reverse. A way to also write this is with two half arrows like this. And so this is the symbol that we use when we want to say the reaction is reversible. And this is sometimes an annoying thing to find in a word processing program. It's in the equation editor in Word, this type of arrow, but sometimes it's easier to find in your symbols. Sorry. Arrows that go, two full arrows going in opposite directions. So let's kind of look at this over time. So this helps me. Let's take this reaction. We have carbon dioxide and water combining to form carbonic acid. Now, as these reactants start colliding in the right orientation for the right amount of energy, they'll form something new. They'll form a product. They'll form carbonic acid. And so as that collision occurs and the product forms, we'll start to slowly increase the concentration of our product. And so we'll see this product concentration increase as the reaction progresses. And for our reactants, as they collide and form products, that concentration is going to decrease over time. That decrease in concentration is going to affect the rate of the forward reaction. We learned when we talked about rate laws that the rate of a reaction is dependent on the concentration of our reactants. And as that decreases, the rate decreases. And so we see for any reaction over time that it'll have a rate that's really fast and then it slows down as the reaction progresses. And so the opposite's going to happen with our products. As that concentration increases, the rate of the reaction will start to increase for the reverse direction because more of our products are around, meaning there's more possible collisions. They'll happen more frequently. And then a percentage of them will produce the reactants. And so we can kind of think of the rate then of our reactants decreasing. And for our products, that rate will increase. And I'm showing that with the arrows here. I'm trying to show that my rate for my forward reaction is the only thing that's happening at time 0. And then that's going to start decreasing as the rate of my reverse reaction increases slowly. And we can see that the reverse reaction arrow is getting smaller and smaller. Chemists like to sometimes qualitatively represent relative rates by how big or long they draw their arrows, which is super subjective, but it's kind of actually a nice little note-taking tool along the way. So there's that. So yeah, this is kind of like a slowed down version of a reaction. This time doesn't actually relate to the actual rate of the reaction, but it's just kind of a way of breaking this down and thinking about what's happening on a molecular level when we see a reaction taking place, and then we see the concentrations essentially look like they stop changing. Um, so what we see is that here's a graphical representation of this. And what we're looking at is the concentration versus the progress of the reaction. And we're seeing here rate change, right? So we start with no products at all, and we start with lots of reactants, and that concentration decreases over time. And with that, so does the rate of the reaction. So if this is really thinking of progress of the reaction as time, then what we're seeing at this in this is any one of these points, the slope of the line would be the rate of the reaction. And we could see that it'll have a bigger slope, therefore be a larger rate of the reaction at the beginning. And then by the end, we'll have a slower rate. And so we hit dynamic equilibrium when the rate of this forward reaction and the reverse reaction are equal. And so we can see that kind of here in this highlighted area, that they stop changing. And that's when we've reached equilibrium. That's when to us it's going to look like on a macroscopic view that the reaction's over, just because we aren't seeing change anymore. Now, the thing that's interesting about reaching dynamic equilibrium, and a common misconception, is that when that point is reached, when those rates are equal, it's just the rates, it's not the concentrations. And so we may have a lot more reactants than products, or a lot more products than reactants, or the same amount. And that actually has nothing to do with whether or not we're at dynamic equilibrium. It's really just about the concentrations aren't changing anymore over time. Let's look at some examples of this after we summarize. So we'll see that at dynamic equilibrium, the key part is that the rates of the forward and the reverse reaction are equal. Now, the concentrations of the products and the reactants do not have to be equal. So we'll characterize equilibrium as usually one of two things. There's perfectly equal. We can talk about that too, but so when equilibrium is when those concentrations stop changing, we might see that we have reactants are going to be larger than our products, in which case we would say the reaction favors reactants at equilibrium. So we'll say favors reactants. And we might see that we have far fewer reactants and much more products at the end of the reaction, or not the end, sorry, when we reach dynamic equilibrium. So we would say that the reaction favors products at equilibrium. So if I'm an industrial chemist and I'm working for a pharmaceutical company and I want to make a lot of something, I'm going to want to make sure that my reactions are going to favor products, so that way I can convert as many of my reactants over to products if I want my product, because I'm going to go sell it and make a lot of money. At the same time, maybe there's another reaction that takes place in that same reaction as a side reaction, and it's going to produce some other product that I don't want, that I'm going to have to spend all this time and energy trying to separate from the product that I do want. In which case, I really want that equilibrium to favor reactants, because I don't want to make very much of it. I'd like it to not happen so much. And so a reaction favoring reactants or favoring products is something that we would love to manipulate. And so we'll talk about that with Le Chatelier's principle when we talk about this material. It's like, how can we do something that affects where equilibrium lies, if it's towards reactants or towards products, to benefit our needs in whatever chemical transformation we're trying to do. So let's look at two examples. So here is a reaction that will favor reactants at equilibrium. Here we go. So that means our concentration of reactants will be larger than our products. And so this is a decomposition reaction. We have N2O4, it's wiggling and shaking, and it wiggles and shakes itself apart. And it forms two NO2 molecules. So our initial concentration of NO2 and our will be high, and our initial concentration of that NO2 will be non-existent when we start. And the rate of this reaction will slowly change until we see the the reaction rates stay the same. And then we've hit dynamic equilibrium. And so here we are right here showing dynamic equilibrium. All right. So once we hit that point, then we don't really see the reaction changing anymore. There's constantly products being formed and reactants being formed, but their overall concentrations remain the same. And our concentration of our reactant is higher than our product. And so we'd say this favors reactants. We're not going to form very much NO2. Now, an opposite version of this is if we have something where, and this is a totally different reaction, sorry. We have hydrogen and iodine combining to form hydroiodic acid. Well, someone's a mouthful. So in this case, when we combine our hydrogen and iodine gas, a reaction occurs that produces more products than reactants. And so in this case, the rate of our reverse reaction versus the rate of our forward reaction, so when they become equal at dynamic equilibrium, we will have made more of our products and have a higher concentration of that than we have of our reactants. And so if we took a snapshot of this reaction mixture at dynamic equilibrium, we would see a lot more of our hydroiodic acid around than hydrogen and iodine. Now, for these reversible reactions, like the decomposition of N2O4 into NO2, um, we can see that. So we know that we'll hit equilibrium, we'll have both around, right? And in this case, we'll have more N2O4 than NO2. Now, we can hit that point of equilibrium no matter where we start. So we can start with a flask of N2O4 and we'll reach equilibrium where we have some N2O4 and less NO2. But we can also start with a beaker full of NO2 and it'll combine and form N2O4. And so if we start with that beaker of just NO2, we'll reach the exact same point of equilibrium with the same ratio of N2O4 to NO2. And that's kind of this powerful thing is that it doesn't really matter if you start with all of reactants or whatever you perceive as products. Like how we define what the reactant and what the product is doesn't have an impact on what equilibrium is. That is going to be something that's characteristic for the reaction, and we'll characterize it by that ratio of our products to our reactants and characterize it that way. And we'll know that no matter what concentrations we start with, we're going to hit that same ratio. Now we may have more or less of each individual one, but the ratio of the amounts will always be the same. And that'll be the defining factor of what equilibrium is for a chemical reaction. And it'll be unique to each chemical reaction, but reproducible anytime you create or perform that reaction in a lab.